Welcome back. This will be lecture number 26 of AC253C. We have been discussing timers, and today, before moving on to our next topic, that is interrupts, let's discuss how to program timers in C. Now that we have studied the basics of C language, embedded C, we will try to rewrite some of our programs in C and also discuss using those examples. I will basically also discuss how to use timer 1, because as you know, timer 1 is 16-bit timer and we can create large time delays using timer 1. So let's do a couple of examples first. Okay, we have to write a C program. Write a C program to toggle all the bits of port B continuously with some delay. This will be example 939 of your book. So what we have to do, we have to toggle all the bits of port B continuously with some time delay, the delay is not fixed here, so we can incorporate any delay. We have to turn on all the pins of port B, and after some delay turn them off, then after some delay turn them on, and repeat this cycle. And it's also given that we have to use timer 0 in normal mode, no prescaler, to generate this delay, because there are various methods how to generate a delay. We can use timers, or we can use simple NOP operations, or here we can use for loops, but we have to use timer 0. And we have to write this program in C. It's easy in assembly language, but it is easier to write this program in C. We will see that in a moment. The first thing, when we start a C program, AVR is, we include the AVR IO file, #include AVR IO.h. Then I will start with my main program, void main. Sorry, there's no terminator of it, void main. I will start my program. By now you should remember that all the input output registers like DDRB, like port B, like for example pin C, pin B, are the registers that were associated with the timers, which we have studied in our last class, like TCC R0, TCC R0A, timer control register A, timer control register B, TCC NT0, timer counter register 0, and other registers, for example TCC R1A, TCC R1B, and others. These are all input output registers. And in C, in HTML Studio, we can directly access these registers. That means if we have to put some data in any of these registers, how we used to put the data in these registers using assembly language, we used to put that data in some register using LDI command. For example, LDI R20 any value 0 cross 32, for example. Then we use the out instruction to put the value whatever was in R20 in any of these registers. For example, out ddrb R20. But here in C we can directly access any of these registers by simple statements. For example, if we want to send some data to these registers, I can simply write ddrb assignment operator, and then the number can be in hex or it can be in decimal or binary. If it's hex, I have to write 0x32. If the number was in binary, I have to write ddrb equal to 0b32. In binary is 00110010. And or I can simply send the value in decimal, that's equal to 50. Same thing. Similarly for other registers. And if I have to get the data from any of these registers, I use it in command in assembly. But here I will simply create an data variable that's 8 bits wide, maybe char. For example, I will write char x and then put that value in x equal to any of these registers. For example, pin C, whatever we are receiving at pin C, port C is getting stored in pin C register, and we are transferring that to variable x. Anyways, let's start our program. First of all, I have to make the port B as output port. That I do by sending ones to the associated data direction register. That is ddrb. So I will write ddrb equal to 0 cross ff, then a terminator. And then what I have to do, I have to turn all the pins of port B on, and then after some delay turn them off. Or maybe I will turn some ports on and some ports off, and after delay some pins I will turn on and some pins off, and after some delay the pins that were on will be turned off and the pins that were off will be turned on. Basically, I have to toggle every pin individually after some time. So I can send any value to port B. port B equal to, for example, I will send this data 0 cross 05. That means I am sending 00000101. Then I have to incorporate delay. I will call a function that I will define later. I will call that function timer 0 delay. I can name anything to this. I can give any name to this function. Then I have to toggle these bits. That means it becomes 1 1 1 1 1 0 1 0. That's F. 1 0 1 0 is 10. That's A, F A. So port B equal to 0 cross F A, terminate. Then again some delay. I will again call the same function timer 0 delay T0 delay, and then I have to repeat this whole thing. That means these 4 statements should be in an infinite loop. So I will create an infinite loop here, while 1, put all these statements inside that loop, close the main. Now I have to define this function. Also, the prototype this function should go here. That means I will write void T0 delay. Now I have to define this function. So, and now I have to actually create this delay using timers. So what are the steps? The first step is to put any value in timer counter register. That means I have to put TC and T0 any value. So I can put any value between 0 and 255. For example, 0 cross 3F. Then I have to put some values in timer control registers A and timer control registers B. That will depend upon which mode I use and which prescaler I use. Since I use normal mode, so timer control register A of 0 will get 0x00. I have explained this thing earlier. And timer control register B will get 01. When I put 101 in timer control register B, timer will start. Then I have to actually check whether the timer overflow flag is set. I can simply write while TOV0 equal to 0, remain here. Until it is 0, I will remain here. I'm terminating the while loop here only. That means there is no statement inside it, so it will keep on checking this condition. Once this condition is met, I will go outside this loop, and that means timer overflow flag has been set. Whenever timer overflow flag has been set, what I have to do, I have to stop the timer. TCCR0B equal to, by putting 00 in timer control register B, and again now I have to actually set the timer flag. So I can simply write TCC TOV0 equal to 1. This is my whole program. Now, this is a very important thing. Sometimes accessing these bits individually don't work. So how do we access them? We access them using our logical operations and shift registers. For example, I know that TOV0 is a bit in TIFR0 register. I have my TIFR register. And the last bit is timer overflow flag 0. So what I can, instead of writing while timer overflow flag equal to 0, I can modify it a bit. I can write while. We have discussed these things, how to use and bitwise and bitwise or. I can use while TIFR0, and I will bitwise and it with the number 0B00000001. And this whole thing should be equal to 0. Are you getting my point? What I am doing, instead of writing timer overflow equal to 0, that is checking timer overflow is it equal to 0 or not. How I am checking timer overflow is 0 or not? Because I know timer overflow is part of TIFR0 register. I am bitwise ANDing TIFR0 register with a number, which actually makes all the bits of timer TIFR0 register 0. That means this bit will be 0000000. The last bit will depend. If it was originally 1, it will remain 1. And if it was originally 0, it will remain 0. That means if the timer has not overflowed yet, it will be 0. And when I will OR it bitwise OR this thing with this number, the result will be 0. That is, my condition will be satisfied. and whenever there's an overflow, this bit will be 1, and when I bitwise or this register with this number, then the result will be a non-zero number. So I will get 0 0 0 0 0 0 0 1. My condition will not be satisfied and I will get out of the loop. I can further modify this statement. I can write something like this while, because this seems messy writing 0b and then 7 zeros and a 1. I can simply use a shift operator. I can write while TIF R0. I am ending it with 1 shifted by here I don't have to shift it because 1 means 0 0 0 0 0 0 0 1 shifted by 0. Sorry, that I have to equate to check it, that should be equal to 0. Actually, this is the more standard way of writing. If this bit was situated anywhere else in this register, maybe here I would have written 3 here, then it would have shifted the bit thrice and we have got the number 0b00000100. Or sometimes if we don't know the position of this bit, I can write while TIFR0 and shifting it using the name of this bit, TOB timer overflow flag 0 equal to 0. Similarly here, since I have to put a 1 here, I will put 1 in TIFR register. So I can put TIFR 0 equal to 1. That's the same thing, putting a 1, or more generally I can write 1 shifted by number of bits that's given by timer overflow flag. That is actually 0, because timer overflow flag has a 0th position, it's the 0th bit. These are the more general ways. You should go through these programs which actually discuss these bitwise operators. We have already discussed these things in one of our previous classes, and these shift operators. Then if you have any confusions, we can discuss in the Zoom session. So this is actually more easy to write programs in C. Let's take another example. For example, this will be example 941 of your book, slightly modified. We have to write a program in C or assembly language programming. There's a LED is connected to port B.4, and we have to blink this LED. We have to keep it on for 1 second, and then we have to turn it off for 1 second. We know that the crystal frequency attached to this system is equal to 16 megahertz. Let's do it using C programming. First thing, we have to incorporate delays that we will do using timers. So first thing we will check is timer 0. Can we generate 1 second delays using timer 0? Since crystal frequency is given and it's equal to 16 megahertz, timer or the time period will be equal to 0.0625 microseconds. And if we use the highest prescaler, that is prescaler of 1024, what will happen to the time period of the timer? That will be multiplied, the frequency will be divided by 1024, and the time period will be multiplied by 1024. That is, the time period of timer will be equal to 1024 into 0.0625 microseconds. That comes out to be 1024 multiplied by 0.0625, 64 microseconds. So what is the maximum time delay we can get using timer 0? Since that's an 8-bit timer, the maximum time delay will be 256 multiplied by 64 microseconds. That is 512, 1024, 2048, 4096, 8192, 16,000 something. Let me calculate it again. (256 into 64), 16384, 16.384 milliseconds. But what is the desired time delay here? 1 second. That means I can't use my timer 0 even using the highest prescaler. What I have to do now, I have to shift to the timer 1. Since my timer 1 is 16 bits wide, so maximum time delay will be 2 raised to power 16 multiplied by 64. 2 raised to 16 is actually f. That means 65536 into 64 microseconds. That means the maximum time delay I will get will be equal to 4194304 microseconds. That means 4.19 seconds. This is the maximum time delay. In fact, the maximum time delay I can incorporate using Atmega 328 microcontroller when I know a 16 megahertz crystal has been attached to it. This is the maximum time delay I can generate, 4.19 seconds. I hope the calculations are correct. So now, since I only need 1 second time delay, I have written 1 second here. Yes, on for 1 second and off for 1 second. So let me use timer 0 with a prescaler of 1024. Each machine cycle gives me a time period of 0.0625 microseconds. This is the time period of the machine cycle time period. Since I am using 1024 prescaler, time period of my timer will be again 1024 into 0.0625 microseconds. That is equal to 64 microseconds. Now the third step, that's that number n. Since I need 1 second time delay, that is my desired time delay, divided by time delay generated, or the time period of the timer, that's 64 microseconds. Divided by 64, this is in seconds, this is in microseconds. I will get the answer here is, that means 10 raised to power 6 microseconds. 10 raised to power 6 divided by 64, answer is equal to 15625. So and then I have to change this 15625 in hex. Let me again use my calculator. 15625 in hex is 3D09, and then I have to subtract it from F, 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 because you see in here, since the timer is 16 bits, the maximum value will be F, 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 F. So F, F minus 3D09, F minus 9, that's 7, F minus 0 is F, F minus D is 2, F minus 3 is 12, that's C, C2F7. That means this value I have to load in timer counter register 1. Timer counter register 1. Let me start my program now. The program is very simple. I will be starting with hash include avr io.h, and then I have to use a subroutine. I'll be writing its prototype here. Void, I will call it t1 delay. I can call it anything again. t1 delay. I will start my main program. What's my main program? I have to toggle bit 4 of port B. So first I will actually make the port B as output. In fact, I have to make only one bit as output, but here I can make the whole port as output. But again, the best practice would have been to make only one bit output. So ddrb equal to ddrb and 0b. I have to make one port output. I can simply, there are various methods. Let me pause here for a second. I could have simply written this thing, ddrb equal to 0 cross ff. Using this command, the whole port would have been the output port. That's I am writing once to the whole port. But since I need only one bit to be output, I don't have to alter the status of other bits. So I again will use bitwise operators to make pin 4 of port B as output, and I won't touch the rest of the bits. So I have to write one to one particular bit. That means this is my ddrb register. This bit 0 1 2 3 4 6. I have to write 1 here, but I don't have to change other bits. So which bitwise operator I will use? And or. If I use and, for example, I do something like this, ddrb equal to ddrb and 0b. Since I don't have to change the status of any of these bits, so maybe I will write 1 1 1 what, and I again have to write 1 here for the to make pin 4 of port B as to actually write 1 to the pin 4. But if there was a 0 already, so ANDing won't matter, because if there's a 0 already, if I AND with 1, it will again become 0, because 0 and 1 is 0. So I won't be using AND operator, but I will be using OR operator. We have discussed this thing also. Whenever we have to set a bit, we use OR operator. Whenever we have to reset a bit, we use AND operator. So DDRB. Now the question is, with which number we are it. Since I don't want to alter the states of other bits, so I will be ANDing it with zeros. 0B 0 0 0. Then since I have to set this bit, I will be ANDing this bit with 1 and all the other bits with 0 again. So when I will OR DDRB register with this number, this bit, this bit, this bit, this bit, this bit, this bit, and this bit, they won't change because I am ORing with 0. If there was already a 0 here, it will remain as 0. If there is a 1 here, since I am bitwise ORing it with 0, it will be 0. But regardless of whatever was here at bit 4, the output will be 1 because I am ORing it with 1. So I can write a statement something like this. DDRB equal to 0B 0 0 0 1 0 0 0. Sorry, I have to bitwise OR it. DDRB equal to DDRB bitwise OR with 0B 0 0 0 1 0 0 0 1 0 0 0. Or instead of this, I can use the compound operator. I can simply write DDRB OR equal to 0B 0 0 1 0 0 0 0. This is the same thing. This actually means that DDRB is equal to DDRB or this number. Same thing. So I can wrap this statement instead of write this statement. Or again, I will rewrite this statement. I can write DDRB or it with what? With a number. That number is 0B0010000. This number I will rewrite. I can simply write 1 shifted by 1 2 3 4 because I have to set the fourth bit. So actually 1 shifted by 4. 1 is simply 00000001. So 1 shifted by, in fact left shifted 4 bits will give me 00010000. This one shift, this second shift, this third shift, this fourth shift. So 1 shifted by 4 will actually give me 00010000. So I can simply write DDRB or with DDRB equal to DDRB or with 1 shifted by 4 bits. This is similar to this, and this is actually similar to DDRB equal to DDRB or 0B 0010000. Or alternatively in Atmel Studio I can write DDRB or equal to 1 shifted by PB4. Just to make it clear that I am actually dealing with 4th bit of port B. This is again the same thing, but some compilers won't allow this. So this is fine, you can use this thing. And this is actually the better practice than writing these big numbers. In fact, the aim here was just to make it the output port. So let's focus on that. So I will write DDRB compound operator equal to DDRB or with what number? 1 shifted by 4, simply. Then what I have to do, I have to toggle this bit again and again with some delay, because there is an LED. I have to turn it on, I have to turn it off. That I will do in an infinite while loop, because I have to do it again and again. Here again I will simply use port B is equal to port B simply toggling the bits. XORing, because XOR will toggle. If it is 0 and I'm XORing with 1, it will become 1. If it is 1, I'm XORing with 1, it will become 0. So this is XORing. I'm XORing, bitwise XORing. With what number? Again with 0 0 0 1 0 0 0 0. That I will write like this: 1 shifted by 4 or PB4. Same thing, 4 or PB4. This will actually toggle the 4th bit of port B. And then I will incorporate the delay. Now I have to define this delay, but using void t1 delay using timer 1, and we have already calculated the value. We need to put in its timer counter register, that's C2F7. Now you should know, since timer 1 is a 16-bit timer, it has 2 timer counter registers, because each register is 8 bits wide. We have timer counter register low and timer counter register high, TC1, T1H, and we have TC and T1L. The higher byte here, that is C2, will go into timer counter register 1 higher. I will put C2 here, and the lower byte F7 will get in the other timer counter register F7. Now I have to start the timer counter register by putting TCCR1A and TCCR1B with some values. So TCCR1A will obviously get 0 0, because again we are using normal mode, and TCCR1B will most probably get 0 0 0 0 1 0 0 1 1 1 1 1 0 1 0 1. That means this is 0 5. To start it in a prescaler mode with a prescaler value equal to 1024. Then I will keep on checking the timer overflow flag 1, that's a part of TIFR1. Again the same thing we discussed in last program, TIFR1 bitwise AND with 0 cross 1 or simply 1 shifted by 0 bits, V1 equal to 0. Until it is 0, we will be in the loop checking it again and again. Once it becomes 1, we will come out of the loop, stop the timer 1, TCCR1B equal to 0, and set the timer flag again, actually clear, by putting a 1 into it. TIFR1 equal to 0 cross 1 shifted by 0 bits, TOB1, clearing timer overflow flag. Then again start the program. So this is my program. I am generating a time delay of 1 second. I am turning the LED on for 1 second, and I am turning the LED off for 1 second. I think we have learned many things using this program. We have learned how to use timer 1. There are two counter registers. Everything else is same. We have also used the how to use these shift operators and bitwise operators to actually manipulate individual bits of IO registers. I think that's it for today's lecture. Thank you.